Introduction to astronomy. And this evening we have Jonathan Park, who's been a guest speaker on a number of occasions, comes up from Hamilton, especially to do the talk. So thank you, Jonathan. Nice warm welcome. Thank you very much.
Thanks, Phil. Good evening. Thanks for coming along tonight. And tonight's talk is the building blocks of the universe and how they relate to astronomy. And that includes the smallest particles that make up everything we can see. Now, I used to find particle physics just as interesting as astronomy and kind of got into both of them and found that, luckily for me, they both fit together very nicely. So tonight's talk mixes them both together. Now, I'll start off very easy with a question. What are you made of? Can anyone tell me? Starts with A. Yes, very good. Atoms. Okay, that's too easy. But we'll start easily. But then you might say, what are atoms made of, and what are the components of atoms made out of, and then how far down the rabbit hole can we go? So we'll find out tonight. It's not too far. But to start off with, I just want to introduce the concept of energy and mass, which is an important part of, well, most physics and astronomy and particle physics. And we'll start with Einstein's famous equation E equals mc squared. And so what does this mean? It means that energy and matter are interchangeable, and it tells you what you get when you convert one to the other. So if we break down the equation, M stands for mass, a certain number of kilograms, for example 1 kilogram. C is the speed of light, which is 300,000 kilometers per second, or 300 million meters per second. And then we square that, so C times C is 90 million billion. And that's better written as 9 times 10 to the power of 16. What that means is 10 times 10 times 10 times 10, 16 times, saves you writing all the zeros. So that's a scientific notation, which you'll see quite a lot with very big and very small numbers. And multiply them all together, and we get the amount of energy that much matter would convert to. So in this example, 1 kilogram, if we convert that whole lot of that kilogram into pure energy, we'd get 90 million billion joules of energy. And just to explain what that, give an idea of what that actually means, if we have a 28 watt LED light bulb, which is LED, so quite bright, it would light up a fairly small room quite nicely. That uses 28 joules per second. So with that 1 kilogram turned into those 90 million billion joules, we could run that light bulb for 100 million years. So that's the energy from 1 kilogram. It's not that easy to turn a kilogram into energy without colliding with antimatter, but that just shows how much energy is contained in a kilogram of mass. So the talk tonight, I'll start with atoms. What are they made of, and how big are they? Then we'll have a look at the smallest particles, going down that rabbit hole to see what we can find. Armed with that information, we'll go out into space and have a look at the sun and beyond and apply this to astronomy. And then we'll end with a mind-blowing fun fact, which is quite fascinating when we get to that. Right, atoms. So everything we can see is made of atoms. That includes stars, planets, rocks, gas, dust, humans. And the average human has about nearly 10 octillion atoms, so that's a 1 followed by 28 zeros. That's 10 billion atoms. That would probably be about a 100 kilogram person, so most people would be under that. So that's a lot of atoms per human being. And of course, atoms can be put together to make molecules. For example, H2O, the water we drink, which is 1 oxygen atom and 2 hydrogen atoms, or O2, the oxygen that we breathe. So the H2O, I think, yeah, that's the water we drink. O2, the oxygen we breathe, 2 oxygen atoms. That next one is methane, CH4, with 1 carbon and 4 hydrogen atoms. And that list goes on very, very far. Now, this is an old way of picturing an atom. A central nucleus made of protons and neutrons surrounded by electrons orbiting like planets orbit the sun. The protons are a positively charged particle. We call it +1 or +1e. The neutrons are neutral, as you can tell by their name, and electrons are negatively charged. And the charge of the electron we call -1 times E, which is the charge of the electron. So it's actually a bit more complicated than that. There's a certain number of coulombs, but we'll just call it -1 for an electron, +1 for a proton. Now, in reality, the nucleus of an atom is tens of thousands of times smaller than the atom itself. And in the case of helium, which is what this is depicting, about 80,000 times smaller. Also, in reality, the electrons don't orbit the atom like planets around the sun. They're actually in a kind of a fuzzy cloud surrounding the atom. So that's the modern way, a more modern way of looking at an atom. The nucleus itself is probably more like a water droplet where the protons and neutrons kind of melt together, but that's fine to think of it that way. And if you remember from the period, question?
Yeah, I have a question. So the reason they create a cloud, is that because electron orbits really fast? It looks like a cloud.
No, it's actually because it lives in what they call a probability of position cloud. So it's quantum mechanical, and so it's a bit like a standing wave. So if you imagine a standing wave, but in 3 dimensions, so the electron is kind of spread out with the probability of being in each position, and it kind of ends up as being a kind of a cloud. You get different shaped clouds for different levels of the electron, but it's a good question, yeah. So, and that clarifies that quite well. And now the smallest or the simplest atom is hydrogen, which, yes? Yeah.
You know how you said everything you see is atoms, but when I put on my, light refracting glasses and I shine a UV light, I'm looking at photons, right? Not...
That's right. The photons, though, are coming off the atoms. So what you're seeing, the photons are the carrier of the light, but you're actually seeing the atoms. Well, I suppose specifically you could say that you're seeing the photons, but the photons only are coming from atoms. So if you take it to the next step, you're really saying that we're seeing the atoms. So things like dark matter are something that we can't see, and it's not made of atoms. So it's the part of the universe that's made of atoms is what the light reflects off or comes from.
Okay.
Now, the smallest or the simplest atom is hydrogen, which is 1 proton and no neutrons. And the next one up is helium, 2 protons and 2 neutrons. If we go further along the periodic table, carbon with 6 protons and 6 neutrons. But further on, iron with 26 protons and 30 neutrons. There's over 100 elements in the periodic table, and each is a different type of atom. And just how small are atoms? This shows the first 3 centimetres of a ruler, and that little red line there is 1 millimetre, which we're all familiar with. Now, even smaller is a nanometre, which is 1 billionth of a metre. So, looking at the average size of atoms, they're all different depending on the size, on the type of atom, but on average, an atom would be about 1/4 of a nanometre in diameter. So that's 1/4 of a billionth of a metre. And that's so small, you need about 4 million lined up to make that 1 millimetre line. And the nucleus, which is super small, is about 0.000005 of a nanometre, incredibly small. And you need about 200 billion of those lined up to make a 1 millimetre line. So in everyday language, just remember those are just ridiculously small particles. And to give a good idea of the size of the nucleus, probably a model is a good way to look at it. And so this is a model of a helium nucleus with our 2 protons and 2 neutrons. It's about 13 centimetres across. Now, if we could blow the atom up to be this size, well, if we could blow the atom up so that the nucleus was this size, the atom itself, the helium atom, would be 10 kilometres across. So it would be 5 kilometres in each direction. And so if we were standing at the top of the Sky Tower holding this little model here, the electrons would be over at the North Shore. And so that's so much space, you could fit about 500 trillion of these into the helium atom. Each atom's a little bit different. The bigger atoms, maybe uranium, might be only 10,000 times, 10 times the size of the atom. Helium, about 80,000. So that just shows you how much space is inside an atom, or empty space. And so that's just given us a quick overview of atoms. So in summary for the atoms, a tiny nucleus made of protons and neutrons, surrounded by a cloud of electrons, with the simplest atom or simplest element or atom being hydrogen with the 1 proton, and the second simplest being helium. So now we'll go down to the next level and we'll have a look at the smallest particles down the rabbit hole. We've seen the electron and the proton and the neutron. Now, in fact, the electron is one of the smallest particles. It's actually what we call a fundamental elementary particle, so it's not made up of anything smaller. It's so small that it doesn't actually have a defined size and is often called a point particle, so you can't get any smaller than an electron. Protons and neutrons, on the other hand, are made out of smaller particles called quarks. Now, quarks, like electrons, are, can anyone answer that one? Elementary particles, perfect. Elementary particles as well. Now, quarks got their name from this man here, this physicist, Murray Gell-Mann. He read a poem, and one of the lines was, 3 quarks for Mr. Mark. And because there were 3 quarks, I don't know what quarks were in the poem, but there were 3 of them, and he thought quark was a good name for an subatomic particle. So he named these things quarks. Another scientist at the same time also came up with the idea that protons and neutrons should be made of 3 particles, and he called them aces. But obviously the quarks won out as the name. And the quarks are up quarks and down quarks. We call these flavors. So there's up-flavored quarks and down-flavored quarks. So you can see the difference between the proton and the neutron. They're almost identical. So a proton is made of 2 up quarks and 1 down quark, while a neutron is made of 2 down quarks and 1 up quark. So virtually identical except for that flavour of one of the quarks. So that's taken us down to that next level. We now see the electron and the quarks as fundamental elementary particles. Now I just want to have a quick look at electric charge here again. We know that electric charge comes in 2 types. There's positive and negative. Opposites attract and want to pull each other together to give a neutral unit, and the universe kind of likes neutral things. So they attract, whereas positive and positive or negative and negative will repel. So try to push those together and you'll find they'll want to push apart. And looking at electric charge, let's have a look at why protons are positive and neutrons are neutral. This comes down to the charge of the quarks. So why we call a proton +1, an electric charge of +1, an up quark has a charge of +2/3, and a down quark has a charge of -1/3. So all we do is just add the charges of the quarks together, and a proton ends up being +1, or a positive charge of +1. And the neutron, it's the same kind of thing. Because it's got 2 down quarks, we can add 2/3, -1/3, -1/3 equals 0. So it's these quarks inside these particles that give them the charges of positive or 0. And electric force, as we saw before, it'll actually decrease with distance. So the further apart 2 electric charges are, the weaker the force between them gets. So get them really close, the force is really strong. Further apart, the force seems to disappear. Now there's another force called the strong force. The strong force is, as the name suggests, a strong force. Now it has a very clever name, obviously. Someone didn't really think too hard about that. But the strong force, unlike the electric force, will actually increase with distance. So it's a bit like a spring or a piece of elastic. So if you get a particle with a strong force charge, which we'll look at soon, so the electric force, of course, has the electric charges. The strong force has different types of charges. So if you take 2 particles with the strong force, pull them apart, it'll get harder and harder to pull them apart, and they'll just want to get closer, just like a spring, as I say, or a piece of elastic. And the charge that these quarks have is what we call the colour charge, and the colour charge is the charge of the strong force. So we had positive and negative for electric charge, and we have something called colour charge for the strong force. So the quarks have this colour charge, and they like to continually swap the charge. So unlike electric charges, which don't get swapped between particles, these colour charges are being swapped between the quarks constantly. And I should point out that it's not actually colours, so quarks don't actually have colours, it's just an analogy, and it works well. We could have used paper, rock, scissors, or cat, bird, mouse, or any 3 things at all. But colours are the best analogy, and I'll show you why in a second. So colour charge comes in three kinds: red, green and blue. And if you're familiar with mixing colours of light, if you mix a red light and a green light, you'll end up with, actually I jumped ahead of myself there. So different colours will attract. So just like different charges will attract of electricity, different colour charges will attract. So red and green will attract, green and blue will attract, and blue and red will attract. And as I was starting to say before, if you mix colours of light, you'll find that red and green make yellow, blue and green make cyan, and red and blue make magenta. If we were to call white neutral, you can see that none of those two together would make white. But if we take red, green and blue and mix them together, we can say that we have white. Now it's a bit like on a TV screen where you have the pixels, the red, green and blue. When they're all lit up, it look like white. So that's why colour is such a good analogy when we've got three types of charges that we want to have together to make a neutral unit. And like I said before, we could have cat, bird and mouse and just define that as neutral, but the colours are just much easier to remember and to think about. And it's the swapping of these colours that give us the strong force and hold the quarks together in the neutron or the proton. And these are swapped by the use of another particle called a gluon, a bit like glue, not to be confused with Klingons. So gluons are a particle which transfer the colours between these quarks, or the colours between the quarks. How it works is if we look at a couple of quarks here, an up quark and a down quark, and they want to swap, say, their red and blue charges. So here we are, we're swapping a gluon, which is swapping the colour in between. And with the two up quarks, have a look at another example, swapping the blue and green. And so these quarks are constantly swapping these colour charges. But the gluons actually have no mass, a bit like photons of light, and so they move at the speed of light. So I've just drawn them as kind of a blurred line. So these gluons are just moving at the speed of light between the quarks and swapping the colours. But in addition to that, gluons attract gluons. So we find that they're best thought of as kind of pulling towards the centre. So you kind of get this Y shape of this gluon flux tube. So the gluons are shooting between these quarks at the speed of light, swapping these colours and holding these quarks together, forming the neutron or the proton. But also quarks move near the speed of light, so they're moving super fast. So this is an animation from MIT, and these three blobs at the end of the quarks, and the glue-like thing between is the gluon flux tube. Now, because the quarks are moving around near the speed of light, that would still be slow motion even there. But I think what's amazing is to think of the fact that that's happening inside all of your protons and all of your neutrons and all of your atoms right now. And in fact, in all of the protons and neutrons of every atom in the universe, this is going on right now, this amazing little system of particles. These three quarks are called valence quarks. And as I mentioned before, that's called a gluon flux tube, holding them, or with the gluons passing between the quarks. But there's actually even more happening inside your protons and your neutrons. The gluons, as they travel between the quarks, actually split for a moment into a quark and an antimatter quark, and then almost immediately turn back into a gluon and carry on their way. And this is a depiction, again from MIT, of millions of these things called C quarks, because they're like a sea of quarks living around those valence quarks. So these quarks are popping in and out of existence constantly inside your protons and neutrons. They're called C quarks, but they're what we call a virtual particle, so they just kind of borrow energy from nowhere and give it back, and so only last for a very short time. So that means inside all your atoms, you've actually got little pairs of matter and antimatter particles appearing and disappearing constantly. And even further out, if we looked at the whole picture of the proton or the neutron, it's really just a whole bunch of gluons, or like almost a cloud of gluons. Not like the cloud of electrons, but more just lots and lots or millions of gluons flying around at the speed of light. If we just zoom back in again to have a look at those C quarks, and then right down to the valence quarks there. So these are real particles, and those other quarks are called virtual particles, those C quarks. So we saw the strong force before. helping these quarks stay together. We actually call that the fundamental strong force. And so you might wonder if a proton and a neutron, well, two protons I should say, are both positively charged, they'll obviously want to push away from each other. So you might wonder how two protons could ever stick together in a nucleus. And a bit like Velcro, there's something called a residual strong force, which just goes out of the particle very slightly, so that it might be harder and harder to get them together, but just like Velcro, once they get close enough together, they'll stick, and that will be much more powerful than the electric force trying to pull them apart. And so that's how you can also imagine two neutrons, of course, why would they stick together? It's the same kind of thing. So this residual strong force is just this fundamental strong force just leaking outside the proton or the neutron very slightly. And that's how we get the nucleus holding together in the center of the atom. So I just want to have a look at one more particle before we head out into space. So we've seen our up quark and our down quark, and it is actually possible for an up quark to transmute into a down quark. What happens is that the up quark can emit something called a positron. Now you might have heard of a positron before, maybe on Star Trek or something like that. It's just the antimatter version of the electron. And so it's identical to an electron except it's got a positive electric charge. So when an up quark turns into a down quark, it emits a positron and another particle called a neutrino. Now this particle called the neutrino, that's the Greek letter nu, which is a good shorthand for a neutrino. These neutrinos have mass, but they're very, very light particles, and they will travel nearly the speed of light. So when this happens, a neutrino will be created and will shoot off near the speed of light. So if we just have a quick summary now of these small particles, we saw the up quarks and down quarks that make up our protons and neutrons. We saw the electron, and then we've just seen the antimatter version of the electron as well. And we saw the neutrino that gets formed when an up quark transmutes into a down quark. Now, a down quark can also transmute into an up quark, and when that happens, we get something called an antineutrino shooting out. When an antineutrino shoots out, it's virtually the same as a neutrino, and it will head out into space just going near the speed of light. In fact, you've probably got about 4,000 or 5,000 antineutrinos coming out of your body now every second as something called potassium-40 decays into calcium-40. And potassium-40 it's not dangerous at all. It just turns into calcium-40 when one of the neutrons turns into, or proton turns into a neutron. Now what happens there is that it produces these antineutrinos, so you've got about, like I said, 4,000 or 5,000 of those coming out, and some of this also causes some gamma rays to be formed, so I think about 200 gamma rays per second come flying out of us. Now that might sound kind of scary, but it's such a small number compared to what's out there coming in all the time that you virtually couldn't even detect it. So there's a lot more happening with our atoms than you'd ever imagine. Now at this stage I thought it might be nice just to take a quick break since we're talking about particles and have a look at a 2-minute video on the Large Hadron Collider. Now if you've heard of the Large Hadron Collider, you might know that it crosses the border of France and Switzerland near Geneva. And the collider is what's large, so Large Hadron Collider means the large collider of hadrons. A hadron is a particle made of 2 or more quarks, so protons and neutrons are hadrons. Now the ring for the Large Hadron Collider is about 27 kilometres around, and I'll show you in a minute how they get the protons into the ring so they can collide them to see what happens. Just before we do that, we'll just have a look. Here the protons are sourced from a bottle of hydrogen. We take the protons from hydrogen gas, use an electric field to strip off the electrons, send the protons through, accelerating them in stages until they eventually get transferred to those big beam pipes of the 27 kilometre circumference. One lot going around one way, the other going around the other way, and then they'll collide them when they want to. These actually go around the pipes for hours and hours with about 40 million collisions per second. So it's just constantly colliding and getting data. So I'll just run this video quickly and show you. So 40 million collisions per second. When they collide, they're travelling at 99.999999% the speed of light. And there's 4 main detectors or experiments. So it zooms right into the start here where we get our hydrogen, strip off the electrons, start accelerating them around a very small booster. Then a next stage a bit faster, giving them more energy. Until finally the last step, where they're going at just about the speed of light, not quite the speed of light because they can't go at the speed of light, and then collide them at a rate of about 40 million collisions per second. These little dots just represent data being collected and sent to the main data centre. And working out what's happening is a bit of a statistical thing, and you'll see a graph in a minute where you kind of look for bumps in statistics and statistical data to find new particles. For example, the Higgs boson that was found a few years ago. And apparently just recently they've just upgraded, so it's got a little bit more energy now than it had previously. So we'll see what they can find in the next few years with high energy collisions. Okay, that was a bit of a break just to see how the Large Hadron Collider works. You can actually find that on YouTube, and there's a few other videos on YouTube which give you a bit more idea of what they do there. And I think even a couple of tours of the machinery. Now, into space now that we've had a look at particles, let's see how we can apply these to astronomy. This is a picture of the sun taken at night through the Earth. Now, it was done over about 500 nights. So it's not a photograph taken with photons, so it's not taken with light, but it's taken with neutrinos, which are those little particles we saw before. Now, neutrinos don't react with much at all. In fact, they interact so little that you wouldn't even know that if you stuck your thumb out now and say the sun was under the Earth somewhere, there'd be 65 billion neutrinos flying through your thumb every second from the sun, created about 8.5 minutes ago. And so if you imagine how many are coming through the room now, just a constant stream of neutrinos. If you could see them, you wouldn't see anything else. Now, they're very safe, of course. That's been happening since the sun started. So let's have a bit of a look at where these actually come from. This is the sun, and this white part in the centre is the core. Now, the core is essentially a nuclear fusion reactor where every second 600 million tonnes of hydrogen is converted into helium. And out of that, about 4 million tonnes per second is converted into pure energy in the form of gamma rays and neutrinos. That little dot there just shows the size of the Earth compared to the sun and that nuclear reactor. So it's a huge reactor. It's so hot that about nearly 16 million degrees Celsius, it's so hot that electrons are torn off atoms. So we have a plasma, a kind of gas of atomic nuclei, mainly protons and electrons, all whizzing around at very high speeds with high energy. So what we're wanting to do in the centre of the sun is we're wanting to convert 4 of these protons into one of these. And you can probably see straight away that there could be a problem here. The first is that we want 4 of these into one of these, whereas there's 2 of these are neutrons, but these are protons. And the other problem, of course, is that protons are going to want to avoid each other, even though when they touch they can join with a strong force, they're still going to be moving past and want to avoid each other, with the electric charge being positive for all of them. So this is an idea of a slowed down idea of the protons moving around in the sun. And what we will find is, if you were to follow one proton, every few billion years, there's a chance that that proton will hit another proton and join up to it. So you might think that's a problem, that it takes a billion years or more for a proton to find another proton, but there are so many trillions of protons in the core of the sun that this happens billions and billions and billions of times, probably trillions and trillions of times per second. And so the protons will, with the help of quantum mechanics and the speed, will occasionally collide and fuse together. The problem is, though, that that's not a stable situation, so then they'll pretty much fall apart straight away. So what we really want is, if we start off with a couple of protons like that, we really want one of these to turn into a neutron, because a neutron and a proton is a stable situation, is a stable particle. It's called deuterium, and it's a heavy hydrogen. So hydrogen has one proton, heavy hydrogen, deuterium has a proton and a neutron. So if one of those could turn into a neutron, we'd be fine. And as you've probably guessed, that does happen, or the sun wouldn't be burning. So one of those protons occasionally can turn into a neutron, and in which case the particles will stay together and we have the first building block of our helium. Now that happens, as we said before, a proton or an up quark can turn into a down quark. So we saw that protons and neutrons are virtually identical except for one of those quark flavors. So what happens, luckily for us, is one of these up quarks will turn into a down quark, so that other proton will turn into a neutron. When this happens, we will have our positron and neutrino emitted that we saw before. The neutrino will shoot off at near the speed of light, and that's those ones that are coming through us now. So they reach us about 8.5 minutes later. The positron will go and find an electron, and as you know, antimatter and matter, when they collide, will turn into pure energy. Well, electrons and anti-electrons will turn into gamma rays, into pure energy. And so by turning the proton into the neutron, we've ended up with a couple of gamma rays and a neutrino. So that was the hard part. Now we've got that done, which is good news. So now that that's happened with all that hard work, it only takes about a second for this particle to fuse with another proton and create helium-3, which is the light version of helium. So that's two protons and a neutron, and we'll get another gamma ray shooting out of there as well. After a while, or a short time, that will find another version of itself somewhere. They'll fuse together with the heat. They'll be thrown together at high speed. That will create helium. Of course, two of the protons will get thrown back into the core of the sun as well. So that's taken us through from protons to a helium nucleus, and that's the fusion process in the center of the sun. And it all happens because, as we've seen now, an up quark can turn into a down quark. These gamma rays will eventually reach us as sunlight. That will happen on average about 170,000 years after they're formed. Now the reason for that incredibly long time scale is that they bounce through and have so much to get through and bounce around that it takes them that 100,000 or so years to eventually get to the surface of the sun. And they lose energy on the way, so that's why we get the lower energy sunlight. But we also get a bit of ultraviolet, of course, and X-rays coming out as well. So the neutrinos, 8.5 minutes or so from forming, these thousands, tens of thousands, 100,000 years before they get to us. And I should say that this reaction only happens 85% of the time. There's a few other things happen the other 15%, but that's the main one, so we don't need to go too much into the other ones. But they will produce some more neutrinos and some more gamma rays as well. And so here we've seen the protons turned into helium, releasing neutrinos and photons. And as I said before, about 200 trillion neutrinos are produced per second. So let's have a look at these matter particles once more, just to remind us. We have our up quarks, down quarks, electrons, and this neutrino. This is actually called an electron neutrino because there's some other types of neutrinos as well. It just so happens that the universe has made another set of particles called a charm quark, a strange quark, a muon, and a muon neutrino. These are not actually needed for anything. They just get formed in high energy situations, such as the start of the beginning of the universe. The Large Hadron Collider has created a few, and with cosmic rays, which we'll have a look at in a moment. So essentially they're exactly identical to these ones up here. They're just much more massive, and they will decay very quickly within a fraction of a second into their smaller counterparts. And if that wasn't enough, the universe has created another set as well, called the top quark, the bottom quark, the tau particle, and the tau neutrino. And again, these are so heavy that they last for even shorter amount of time than these ones. The top quark lives for such a short time that in the Large Hadron Collider, they can only tell that it was there by looking at what it decays into, because it lasts for such a short time. They might have seen a bit more now, but in the past they had to look at what it decayed into by following the lines of particles that were formed. Now these things are actually, like we saw before, called flavors. So we saw the up quark and the down quark were flavors. And so the charm strange and all the other ones are just called flavors. So we have an electron flavored neutrino, a muon flavored neutrino, and a tau flavored neutrino. The neutrinos created in the sun are actually these electron neutrinos, but by the time they get to Earth, they've actually turned into 1/3 of each. So these actually change their flavors as they fly through space. And there was a time when they first were looking for neutrinos from the sun that they knew how many they should find, but they only found 1/3, and were a bit concerned about what might be going on, because of course if neutrinos get to us within 8.5 minutes, and the light takes about 100,000 years from the time that it's created or formed, then if there was a problem in the center of the sun, we wouldn't know for a few 100,000 years, except by looking at the neutrinos. It was only by studying these and working out that they actually do change flavor that they could start looking for these, and found that the neutrinos did add up and the sun was working fine. And of course there's antimatter particles, as we saw before. You don't need to remember them all. It's just the only thing to remember is that each particle, each fundamental particle has an antimatter counterpart, often written with a little bar at the top and with the opposite electric charge. But we don't need to worry about that too much tonight. So let's move on now to cosmic rays. Cosmic rays are not actually rays at all. They are, about 89% of them are protons, about 10% are helium nuclei, and the other 1% are larger nuclei, such as up to iron and even higher, maybe uranium. Where do they come from? Well, we know we get a lot of particles from the sun in the solar wind, and we see those generally when they hit the Earth as aurora, so they get diverted by the magnetic fields around to the poles, so we see the aurora. More powerful or more energetic cosmic rays come from supernova, supernova remnants, the gas and dust which is expelled during the explosion. There's a lot of twisted magnetic fields in these, and from unknown sources outside our galaxy. Now let's have a quick look first of all, or next, at these higher energy particles. So if we look at a supernova remnant, these have a lot of twisted magnetic fields, which as we saw with the Large Hadron Collider, can accelerate charged particles. So charged particles within these remnants will get accelerated out into space, where they will start traveling through space. They'll find other magnetic fields and get twisted and turned, maybe accelerating, going faster and faster, up until they're moving at just about the speed of light. And eventually they will hit something, maybe like the atmosphere of the Earth. And of course there'll be a lot going other directions, hitting other things as well. And coming in from outside is a much faster or much more energetic particle from the outside the galaxy. Of course that would take 100 or 200,000 years, even near the speed of light, to go that distance. And there's a lot of these remnants and things all over the galaxy. So we're getting millions of these hitting the Earth's atmosphere every year. And unlike the ones from the sun, or the lower energetic ones from the sun, these can kind of punch through the magnetic fields and just hit the atmosphere around the Earth at any place at all, even above us right now. Now the speeds of these cosmic rays can be up to 19 nines % of the speed of light. So that's the high energy cosmic rays that hit us can get up to that that speed, that much energy. We saw the Large Hadron Collider is only 99.99999% the speed of light. So we can see that nature is giving us much more powerful particles than we're creating in the Large Hadron Collider. So there was a bit of worry, I think, at the start. Well, some people were worried that the Large Hadron Collider might create a black hole or some sort of event which would destroy the Earth. But if that was going to happen, I think nature would have done that already. I think we're pretty safe with these speeds here. I don't know if it'll ever get up to that speed at the Large Hadron Collider, but if it did, we'd still be pretty safe. So what happens when these hit the atmosphere? Well, the proton, for example, if we look at a proton example, that's called a primary cosmic ray. It'll hit a molecule or an atom in the Earth's atmosphere. And just like in the Large Hadron Collider, it will be going so fast it'll smash another particle into pieces and give a shower of particles. Don't worry too much about what these are, but if you are interested, these are pions, this one's a kaon, and they're made of pairs of quarks and antiquarks. So the pions are made of the up and down quarks that we saw before with the antiparticles. And the strange quarks, one of those heavier ones that I said before, don't really have any use. They will get created in these high energy events. So you get some kaons as well, which these will last for a tiny fraction of a second. Kaons decay into pions. Pions decay into muons. So those muons we saw before, the heavy electrons, and muon neutrinos or anti-muon neutrinos, and various different combinations of these. These muons and anti-muons are also flowing through us now, probably about 1 muon or anti-muon per area of the palm of your hand every second. So they're also harmless, well, pretty harmless, we'd know if they weren't by now. So they're coming through us as well. So as well as all these neutrinos, we've got these muons. Now, I'm not talking about dark matter tonight, but that's probably also flowing through us as well. So it's a lot of stuff happening that we just can't see. Other things happen as well. Pions can turn into gamma rays. They can turn into electrons and anti-electrons, and so on. In reality, there's actually millions of particles created in these air showers. So the high energy cosmic rays, they are the primary cosmic rays, and these are called secondary cosmic rays. These are all the particles that are created and shower the Earth, and so they're called air showers. Occasionally some of these will get all the way through, so occasionally a helium nucleus or a high energy proton will come zapping through. But it's mainly these air showers of particles that are coming through. So now we've been through all that, let's have a look at an even more amazing fact. Well, I think it is. We'll have a look at the mass of a proton. Now, a proton weighs, or the mass is 1.673 times 10 to the minus 27 kilograms. So it's 0.00 with the 1 at the 27th decimal place. Now, that is 1673 quectograms, but we're not worrying about the units. We just want to look at the numbers. So we're just going to look at 1673. The quarks are, the mass of the quarks, the up quark is 4. There's 2 of those, and the down quark is 8.5. And so the total of the quarks, if we take, remember the gluons have no mass, so they're massless. So the total of the particles that make up a proton is 16.5, about 1% of the proton. And so that's all the particles, the rest is just energy. And so this mass difference, this 99% missing mass, just comes, oh, I should say also neutrons, same kind of thing. But it comes from the energy of these gluons, from these massless gluons. We saw Einstein's equation E equals mc squared, which we can switch around. Einstein actually originally talked about mass being energy divided by the speed of light squared. So he was saying if you have a certain amount of energy, it should behave like mass of that much energy divided by the speed of light squared. And to put that in perspective, I suppose if you took a cup of coffee, a cold one, and heated it up, that would weigh more than the cold one. Now, it would be such a small amount we couldn't measure it, but the energy would actually give it more mass. So we find that 99% of our mass comes from energy of these gluons, and only that 1% comes from those particles. So if you look at a human, a 70 kilogram human, only 700 grams of our mass is actually from particles, and the other 69.3 kilograms just comes from energy, the energy equivalent of those particles. So I think that's pretty mind-blowing. 1% of us is particles. But we're not special, so rocks be the same, anything with atoms, same kind of thing. Now, I just added this other bit in, next bit in here because some of you might know about the Higgs field, which I haven't talked about tonight. But just in case you've heard of the Higgs field and heard that the Higgs field gives things mass, the Higgs field is what gives those fundamental particles the mass. So the quarks and the electrons get their mass from that Higgs field. And that's why 1% of us is from the Higgs field and the other 99% is from energy. You don't really have to worry about that, but I thought I should just put that in case anybody kind of had heard of the Higgs field and wanted to know how that related. So just summarising that last bit there, we know atoms are mostly empty space, in fact 99 point that many nines of empty space. And so that means only 1 part per trillion of an atom is something. So if you squeezed atoms, the electrons into the nucleus of the atoms, the whole human race could fit into the size of a sugar cube. That's pretty much what's happening in neutron stars, where the electrons are forced into the protons, forming neutrons, and all that space is squished up into a very small amount, very dense. And that sugar cube would weigh maybe about 500 million tons. So we got down to that sugar cube. And then from what we saw before, only 5 million tons of that is particles and 495 million tons is just from the energy. So although we couldn't actually physically, well, we could if we put ourselves on a neutron star, but we couldn't physically do that. It just shows, what we're made of is not what you'd think. And that actually brings me to the end. So let's just look at a quick summary here. We saw atoms are a tiny nucleus surrounded by a cloud of electrons. We've seen our quarks, electrons, and neutrinos. That's our fundamental particles and their cousins. We've now seen how hydrogen nuclei are converted into helium in the sun, and we've seen cosmic rays, and then we've seen how 99% of our mass comes from energy rather than particles. And that actually brings us to the end of the talk. And if all you remember is the quarks, that's all you need to remember for tonight. You'll probably find when you read a book about it somewhere, you might remember some bits and pieces. And so that brings us to the end of the talk tonight. Thank you. How was that for time, Chris? Is that where? Cool. So a bit of time for questions. Yeah. So if anyone's got questions, I've left out a lot of quantum mechanics stuff on purpose because I thought you might want an introduction rather than a deep quantum mechanics talk. So yeah, any questions anyone has?
So on the said it takes 170,000 years for the
kind of an average. Some will get out pretty
gamma
quick.
ray to get out.
Yeah.
But is it actually that ray exists as an entity the whole time, or is there a constant absorption?
It'd be pretty much
going on?
a lot of absorption and so probably that bit of energy really is what we but it sounds more exciting if you think of this. But no, you're quite right though, because by the time it gets through, it's lost energy, and possibly some cases it's been absorbed and re-emitted as 2 lighter photons to less energetic photons and gets to the edge of the sun. And then it's only 8.5 minutes from there. Yeah.
You said in the core of the sun how there are lots of swirling protons, and eventually a proton will become a neutron. What causes that change?
Now it's something called the weak force. So we looked at the strong force and the electromagnetic force. There's another force I haven't really talked about tonight called the weak force. Now that actually allows quarks to change flavour kind of randomly. Now, why it actually happens at certain times and not other times, I don't think is fully well known. For example, a neutron sitting on its own on the shelf would turn into a proton in about 15 minutes on average. But a neutron attached to a proton is stable. And so why that happens, I don't think anyone's quite sure. But because protons are not stable together, something happens with this weak force, which allows the quark to change flavour. The weak force is called weak because it's very short range, and it works by a couple of other particles called W bosons, or W plus and W minus bosons. So that's kind of the start of how it happens. But have a look up for the W bosons and the Z bosons, and you'd have a read of that and you'll find it really interesting. Other questions?
I have a more silly question. So if one of those high energy protons or helium nuclei that comes in and smashes into the atmosphere actually makes it down here and strikes my arm, is it conceivable that I could feel it?
No, I don't think we'd. No, we've got the muons at least going through us all the time, and I think not enough damage. No, you'd have to have. You'd be getting up to a grain of sand, or well, I suppose a grain of sand going that speed would probably kill you. So would definitely kill you. But I don't know how big you'd have to get to actually feel something. Very high energy, yeah. So usually just goes
DNA damage
and cause DNA damage. So your DNA would notice, yeah, occasionally.
Experience cosmic rays when they close their eyes and there's sort of little flashes in the back of the retina.
And
that was cosmic rays going straight through the craft, but also it would strike the craft and then create a cascade of other particles as well.
Yeah, they had trouble sleeping apparently, yeah.
ISS astronauts report the odd little flashes in the back of the retina at night.
That's right, yeah. Yeah, when they tried to go to sleep, I think every 3 minutes they'd report flashes. It'd be quite hard to sleep if you had your eyes closed and saw flashes every 3 minutes as they passed through. So yeah, you would notice that, I guess. I know that you can get cosmic ray tracks from CCDs, and you get little tracks on those. And when they transported them high up in the atmosphere, or not that high, but in a plane, they would get damaged a little bit at times. You can also make up little cloud chambers. You might see them on YouTube if you have a look. It's a thing, they call it a cloud chamber. You put dry ice underneath, put some alcohol inside, and maybe a black curtain behind it, and watch, and you'll see these little streaks of bubbles appear as cosmic rays. Maybe some are initial primary ones, and some are the muons travelling through. And you can actually see the little lines. So I think you can actually make them at schools and things. They probably do sometimes. But if you put uranium in them, that's amazing, because you see there's just amazing amounts of particles coming off the uranium. So have a look at that on YouTube too. That's really amazing to see.
Do you have a lot of uranium floating around?
Not much, unfortunately. I think I'd be in hospital now if I did. No, it's on YouTube. I'll leave it to the YouTube people. No other questions? I can talk about it all night.
Well, thank you very much, John.
Thank you.
Coming up. Dark, wet night. Thank you
Yeah.
very much, and we look forward to you next month. Thank you.
Thanks very much.